This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 6 of Week 3, Convection Fundamentals, Newton's Law of Cooling, the convection film coefficient H, and the three dimensionless groups that pin H down, Reynolds, Prandtl, and Nusselt. Conduction had one clean material property, K. Convection is messier. Newton's law of cooling bundles everything into a single coefficient, H, but H is not a material property. It depends on velocity, fluid properties, geometry, and the flow regime. The whole job of convection analysis is finding H, and that's where the dimensionless groups come in. Newton's law of cooling, Q dot equals H times AS times the quantity Ts minus T infinity. AS is the surface area in contact with the fluid, Ts the surface temperature, T infinity the bulk free stream temperature. It's linear in the temperature difference. Double the difference, double the rate. One notation note: the handbook uses TW and a plane A. We use TS and AS. Same equation, only the subscripts differ. Unlike K, H is not tabulated as a material constant. It's a result of the flow. But the typical ranges are worth memorizing for sanity checks. The table climbs from free convection in gases at the low end through forced convection in liquids, with boiling and condensation topping it. 3 orders of magnitude separate free air from forced water. One caveat: these are textbook reference values, not from the handbook. Use them as sanity checks, never as an exam answer. Convection correlations link 3 dimensionless groups. 2 are inputs you compute. The third hands you H. Reynolds, rho VL over mu, inertial to viscous forces. It sets the regime. Prandtl, Cp mu over K, momentum to thermal diffusivity, a fluid property at the film temperature. Nusselt, HL over K, the dimensionless convection coefficient, the output. Workflow: compute Reynolds and Prandtl, pick the Nusselt correlation, invert to H equals Nusselt K over L. 2 notes: the handbook's Reynolds uses kinematic viscosity nu, just mu over density, so the forms are identical, and the subscript names the length, REL for a plate, RED for a tube. Convection lives in 2 thin layers that grow along the surface. The velocity layer is where the flow slows from free stream to 0 at the wall. The thermal layer is where temperature shifts to the wall value. Both start thin at the leading edge and thicken downstream. Their relative thickness is set by Prandtl. Velocity over thermal is roughly Prandtl to the 1/3. For air, about 0.7, so the two are comparable. The practical point: H is highest at the thin leading edge and decays downstream. The flat plate correlation gives the average H. Reynolds number decides which correlation applies, with different thresholds for internal and external flow. Internal tube flow, laminar below 2300, turbulent above 10,000, transitional between. External flat plate, the handbook switches at Reynolds L of 10 to the 5th. Use that as the laminar to turbulent boundary. The most common convection error is plugging a laminar correlation into turbulent flow, or the reverse, so always compute Reynolds first. One footnote: the classic textbook plate transition is near 5 times 10 to the 5th, but on this exam, follow the handbook's switch point. The variable table for a flat plate problem, same column shape as the rest of the course. The top 4 rows are fluid properties: density, viscosity, specific heat, conductivity. Then the boundary inputs: free stream velocity, plate length, and the surface and fluid temperatures. The bottom 4 rows are computed and solved for: Reynolds, Prandtl, Nusselt, and finally H. The critical rule: evaluate all 4 fluid properties at the film temperature, the average of surface and fluid. Worked problem: air at 20 Celsius flows at 3 meters per second over a flat plate 0.4 meters long. Surface held at 60 Celsius. Air properties are given, evaluated at the film temperature, the average of 60 and 20, 40 Celsius. Find the average convection coefficient H over the plate. Once we have H, it feeds Newton's law of cooling for the heat rate. Compute Reynolds and Prandtl first. They set the regime and the correlation. Reynolds L is rho times phi times L over mu, about 75,200. Prandtl is Cp times mu over K, about 0.71, just what we expect for air. Reynolds-L is below 10 to the fifth, so it's a laminar flat plate. Apply the laminar flat plate correlation. Nusselt L equals 0.664 times Reynolds L to the 1/2 times Prandtl to the 1/3. Substitute, and Nusselt L is about 162. Invert the Nusselt definition to recover H. H equals Nusselt times K over L, which gives about 10.7. Final answer. H is about 10.7. 4 checks. Units. Nusselt and Prandtl are dimensionless, so Nusselt times K over L gives watts per square meter Kelvin. Magnitude. Forced convection of a gas lands around 25 and below at low speed, and about 11 for this air sits in that band. Regime. Reynolds was below 10 to the fifth, so laminar was the right pick. Payoff. Feed Newton's law of cooling with a 1 meter wide plate, and Q dot is about 171 watts. Small h is exactly why fins multiply surface area when you can't raise it. 5 traps that cost points. 1. Skipping the Reynolds regime check. The wrong regime gives the wrong Nusselt and H. Internal laminar is below 2300, turbulent above 10,000. The plate switches at 10 to the fifth. 2. Properties at the wrong temperature. External flow uses the film temperature, the surface fluid average. 3. Mixing the mu and nu forms of Reynolds. They're equal, so don't divide by density twice. 4. Wrong characteristic length. Flat plate uses plate length, tube uses diameter, and Reynolds and Nusselt must share it. 5. Using the average H where a local value is asked. Local H is highest at the leading edge. Bookmark the convection pages. Newton's law of cooling, the Reynolds, Prandtl, and Nusselt definitions, the laminar flat plate correlation, the internal flow regime thresholds, and the film temperature definition all live together on 3 facing pages. Fold the corner. Newton's law, the dimensionless terms, and the flat plate correlations sit side by side. Up next, Topic 7, Forced convection correlations. Topic 6, Set up the machinery, Newton's law, the Reynolds-Prandtl-Nusselt triad, and the flat plate laminar correlation. Topic 7 puts it to work across the handbook's geometries, turbulent flat plates, cylinders in crossflow, spheres, and internal tube flow with Cedar Tate and Dittus Bolter. The workflow is unchanged. See you there.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.